which is on probably the single most significant meteorological variable, at least for humans, the one that we usually care about the most, which is air temperature. Now, the reason why I say that we care about it the most is if anybody asks you, well, how's the weather outside? Unless it's raining or snowing or unless something crazy is happening, most people are just concerned about the temperature. In fact, if you open up any of your weather apps on your iPhone or your Android or whatever you may have, usually the first thing you'll see, and it's usually highlighted in the largest numbers, is the temperature. So air temperature is actually a very big deal. It's extremely important to human comfort. And as a result, it greatly affects what we wear and the activities that we do. But how do we actually measure air temperature? Now, a lot of people think that, okay, well, if I'm going to measure air temperature, I'm going to go out in the sun and hold a thermometer and that's it. But there's actually a set of very stringent guidelines to how to accurately measure air temperature. And the reason why we have these guidelines is because we want to be able to compare our data to other observations for the purpose of record keeping, for the purpose of scientific research, and for the purpose of just simply making sure that everybody's doing it the same way. And so in order for this to happen, there is an international body of some of the world's top meteorologists called the World Meteorological Organization. And they have, for over the past century, governed how we should measure air temperature. And again, the reason why we want to do this is because if two different people are measuring air temperature two different ways, you can't really fairly compare those two readings. For example, if I live in San Francisco and I measure my air temperature right above the ground, whereas in San Jose, somebody else is measuring their air temperature 2,000 feet above the ground, you really can't make a fair comparison of those two individual pieces of data. So here's how we actually measure air temperature. We measure it in a shaded and ventilated box at about 1.5 to 2 meters above the ground. So essentially the average height of a human in the shade, because we don't want extra sunlight to create an abnormally high reading, and in a well-ventilated box. And the reason why we want it ventilated is because if it's not, we're not getting any of the outside air into it. So that's how we measure air temperature around the world. Now, here on Earth, we've experienced some pretty extreme temperatures. And the highest temperature ever recorded here on Earth was recorded in Death Valley, California on July 10th, 1913. And that was a high temperature of 134 degrees Fahrenheit. Now, there was a previous record that was higher in a city in Libya that was over 136 degrees Fahrenheit. However, upon looking back at the records of that day, looking at nearby temperatures, and also looking at how things were measured, it was determined that that record was inaccurate. That temperature reading didn't meet WMO standards. And hence, we can't say that's the hottest it's ever gotten on Earth. So we had to throw that out. Now, the record low temperature took place at a scientific research center in Vostok, Antarctica on July 21st, 1983. And its low temperature was negative 129 degrees Fahrenheit. So, as you can see here, we have a pretty large variation. 134 degrees is our hottest, negative 129 is our coldest. So, very cold temperatures versus very hot temperatures. Now, how does our temperature vary throughout the day? Well, I'm sure all of you would say, well, it's cold at night and warm during the daytime. But have you ever noticed that it's usually not warmest at noon? No, usually the warmest time of the day is several hours later, usually at 2 to 3 p.m., or even a little bit later than that. Why is that? Well, in order to understand that, we have to remember a few things that we've previously discussed about radiation. So here's how it works. First off, during the day, the sun's out. And so the sun is giving us heat. As the sun is giving us heat, it causes our Earth to warm up. As our Earth warms up, the very, very, very bottom of the atmosphere, I'm talking 1 to 2 centimeters above the atmosphere, or above the ground, 1 to 2 centimeters above the ground, becomes substantially hot. It becomes substantially hot. As this area warms, it causes heat to rise. It causes convection to occur. And that convection then takes heat from the ground, pushes it up into the atmosphere. And so that's how our air warms up during the daytime. Now, consequentially, if you're right near the surface of the Earth, air temperatures can be anywhere between 10 to 15 degrees Celsius higher than just a meter or two above the ground. This is one of the reasons why we don't want to measure air temperature right at the ground. Because a comfortable 65-degree day may come off on a thermometer as more like 85 to 90. So this is one of the reasons why we want to measure a few meters above the ground. Now, at noon, the sun is the highest in the sky, and incoming sunlight is the most intense. So by that logic, you would think, okay, well, noon should be the hottest. But here's the thing, though. Remember, temperature and heating and cooling occur as a result of the budget between incoming sunlight and outgoing terrestrial radiation, outgoing long-wave radiation. At noon, that's when incoming sunlight is most intense. However, it is still substantially greater than outgoing long-wave radiation. As a result, even at noon, the Earth is still continuing to warm. Now, as we transition into the afternoon, the sun begins to get a little bit lower in the sky, but it's still warming the Earth up. So as the Earth is warming up, it's giving off more radiation, per the Stefan Boltzmann law. And so what's actually happening is, after noon, the amount of incoming sunlight is declining. The amount of outgoing terrestrial radiation, outgoing long-wave radiation, is increasing. And that pattern continues to happen until the two equal each other. And that's usually right around 3 to 5 p.m., though it really depends on a few factors: the presence of clouds, the time of year, things like daylight savings time. But for the most part, what happens is, after noon, as the sun begins to lower in the sky, incoming solar radiation, or as we called it last time, insolation, is decreasing, but the outgoing long-wave radiation is still increasing. And then, at some point in the afternoon, the two equal each other. That represents the highest temperature of the day. After that point, solar radiation continues to decline, and it quickly becomes lower than outgoing radiation. So incoming radiation is declining rapidly. Outgoing radiation isn't declining as quickly. So we then have a situation where outgoing is greater than incoming. And just like your bank account, if you spend more than you make, your bank balance decreases. Same thing happens here, and the Earth begins to cool. Now, this can all be summed up in this graphic, and you're actually going to do an exercise that sort of walks you through this process, but let me give you the TLDR version right now. So, at midnight, there's no sunlight coming in. However, the Earth, because it has a temperature above absolute zero, is still giving off radiation. And it's giving off long-wave radiation. Now, as the night goes on, there's still no sunlight coming in, but the Earth is still giving off radiation, so it continues to cool and cool and cool and cool. And if there's no sunlight, it would just continue to cool. Well, then the sun rises, and for the purpose of this graphic, we say the sun rises at 6 a.m. Very quickly, just after sunrise, the amount of incoming solar radiation equals the amount of outgoing long-wave radiation. That represents the coldest temperature of the day. So it's right at sunrise, maybe a few minutes after sunrise. From that moment on, incoming solar radiation is greater than outgoing long-wave radiation. As a result, we now have an energy surplus. Earth begins to heat up. The Earth begins to heat up. Now, according to the Stefan Boltzmann law, as the Earth heats up, more radiation is given off by Earth. So the amount of radiation the Earth is giving off is increasing, and then noon rolls around. At noon, the sun's the highest in the sky, but it's still giving off far more radiation than the Earth is. And as a result, the Earth is still warming. As sunlight after this point begins to decline, as the sun gets lower in the sky, terrestrial radiation given off by the Earth is still increasing as the Earth is continuing to warm, and eventually the two equal each other again. This represents the high temperature of the day. After this point, the amount of incoming solar radiation quickly declines. The amount of outgoing radiation doesn't decline as quickly, but the temperature does begin to drop until midnight. So at night, there's no incoming sunlight. Remember that. At night, there's no incoming sunlight. However, because the Earth has a temperature above absolute zero, it still gives off radiation. As it gives off radiation, it's losing heat. It's losing energy. As a result, it cools. We call that radiational cooling. That's called radiational cooling. Now, what actually happens in the case of radiational cooling, the ground becomes cold rapidly, whereas the air above the ground doesn't cool off as quickly. What this causes is the ground to become very cold and the air above it to stay pretty warm. This creates an inversion, a layer in the atmosphere where going up in height, temperature actually increases. So from the ground up to a few meters above the ground, temperature actually increases. Again, this is also why we don't want to measure air temperature near the ground, like on the ground, because it gets extremely cold at night. And I'm sure you've felt this even on a relatively warm evening. If you walk outside barefoot, the ground is much colder than the air. As the nighttime continues, Earth continues to give off radiation. And then it's coolest right at sunrise. So it looks something like this. Near the surface of the Earth, the air is much colder than it is just a few meters above the air. So this gives us an interesting diurnal variation. And diurnal is just a fancy word for daily. So remember that word though. So it gives us an interesting diurnal variation. And Basically what happens is at night, what you see is the ground is colder than the air above it. And so you get this little inversion at night. Whereas during the daytime, the ground becomes much hotter than the air above it. The air becomes much hotter. The air near the ground becomes much hotter than the air above it. Now, so far we've talked primarily about daily temperature variations. But what about seasonal temperature variations? As we talked about in the last lecture, different locations have different seasonal variations. Some locations have very little difference between winter and summer. Other locations have substantial differences between winter and summer. Some places get snow in the winter, none in the summer. Other places stay hot year-round. Other places are extremely cold in the winter and extremely hot in the summer. Well, what actually determines a location's seasonal temperatures? Well, there are four main things that determine it. Latitude, proximity to water, elevation, and ocean currents. So latitude, proximity to water, elevation, and ocean currents. So let's talk about each one. So, latitude. As we talked about last time, if you live near the equator in the tropical regions, you experience warm temperatures year-round. So, it's usually very warm, temperatures in the high 80s, low 90s even, and very little change from season to season. And this is because the sun is always high in the sky. So there's not really a big variation from season to season. If you live in the mid-latitude areas, you experience warm summers and cool winters. And this is because during the summertime, you get a lot of sunlight. During the wintertime, not as much, but you still get some. And so it's warm in the summer, cool in the winter. So there's some noticeable seasonal variation. However, if you live near the poles, in the polar latitudes, you get extreme seasonal variations. And what I mean by extreme seasonal variations is you can get substantial amounts of sunlight in the summertime. And in fact, anywhere above the Arctic Circle has at least one day where the sun's out for 24 hours. At least one day. And so days are very long in the summertime. However, they're very short, if at all, in the wintertime. And so summertime can become extremely warm, wintertime can become extremely cold. So you get very little variation near the equator. You get some variation in the mid-latitudes, and you get major variation near the poles. And this all has to do with the amount of incoming sunlight and how it changes from winter to summer. If you live near the equator, or if you live approximately on the equator, sun is high in the sky year-round. Same if you live in the tropics. Sun is high in the sky year-round. The further away from the equator you get, the greater the variation is. It's low in the sky in the wintertime, high in the sky in the summertime. And then again, if you live right near the poles, you get no sunlight during the wintertime and extreme sunlight during the summertime. Now, here's how this actually creates seasonal variations. Pay really close attention to these next two slides. So, this first one is a weather map showing average temperatures for January. As you can see, areas near the equator are pretty hot in January. As you go further away from the equator, it gets colder. But notice this. It's not nearly as cold near the South Pole as it is near the North Pole. This is because down here near the South Pole, January is their summer months. Whereas here in the North Pole, this is their winter months. Now, do me a favor. Focus your eyes right up here. This is Siberia. Look at how cold it is in January. Now watch what happens as I switch from January to July. Take a look at that. So going back, in January, temperatures up here near Siberia are as cold as minus 50 degrees below zero. That exact same region has a temperature above 50 degrees Fahrenheit in the summertime. So you get extreme variation. And as you can see, it's not nearly as cold up here in the summertime. It's a little bit colder down here in the wintertime. A lot of this also has to do with land distribution and so on. Well, we're not going to talk about that right now. But again, if you go back, extreme cold near the poles in the wintertime, much warmer in the summertime. Meanwhile, look at the equator. So let's go back to the equator. The temperatures near the equator in the wintertime in January, are in the 70s and 80s. So pretty mild, warm, average temperatures. If you take a look in July, not really much difference. Still 70s and 80s. Not major differences between January and July. So again, the further away you get from the equator, the greater the seasonal variation. Down here near the equator, seasonal variation may only be as little as 4 to 5 degrees Fahrenheit. Whereas up here, closer to the poles, it can be as much as 100 degrees Fahrenheit. So big changes between summer and winter. Now, let's talk about a few other major factors on temperature. Proximity to water. And this is something we can actually see here in the Bay Area, believe it or not. Something we can actually see here in the Bay Area. So here's how this works. Water has a high specific heat. Specific heat is the amount of heat an object needs to absorb to warm up by 1 degree Celsius. Water has a specific heat 5 times as great as land does. As a result, water needs 5 times as much heat to warm the same amount as land does. Consequently, during the daytime, both land and water get the same amount of heat, but the ocean doesn't heat up as much. Simply because it has a higher specific heat. Now, what this creates is an interesting situation where if you live near the ocean, temperatures don't vary much from season to season. And again, this is because oceans need to absorb a lot more heat to warm up, and they need to give off a lot more heat to cool down. So they don't fluctuate in temperature nearly as much as land does. A good case study of this, St. Louis, Missouri, and the Azores. Pretty similar latitudes. The only thing different between these two areas is St. Louis is landlocked, whereas the Azores are islands. And if you take a look, St. Louis has a major temperature range. The difference between wintertime temperatures and summertime temperatures are approximately 50 degrees Fahrenheit. So winters are cold, summers are warm. On the other hand, if you live near the Azores, the variation is substantially lower. It's only 14 degrees Fahrenheit. Now, we can see this here in the Bay Area as well. Compare San Jose to San Francisco. And what you'll notice is that San Jose commonly gets into the 80s and maybe even sometimes into the 90s during the summertime, whereas San Francisco really doesn't. San Francisco stays pretty cold year-round. Now, we'll actually talk more about that when we talk about what's called coastal upwelling in a couple of weeks. The next thing, and this one doesn't take too long to talk about, elevation. Elevation has one simple relationship with temperature. Usually, the higher you go up, the cooler it is. A good example of this is Mount Hamilton, which is just to our east here in Silicon Valley. And Mount Hamilton is home to a beautiful observatory. And the top of Mount Hamilton is approximately 4,000 feet above the valley floor. Sometimes during the winter time, the area near Mount Hamilton can get snow, whereas the hills just below can be a lot warmer, and therefore they don't get snow. This is one of the reasons why if we want to go skiing or if we want to go play in the snow, we want to get away from the lower elevations. This is why we go up into the mountains, why we go to places like Tahoe or Yosemite or places like that rather than hanging out here in San Jose. Like, we don't go up to the Santa Cruz Mountains because they're just not tall enough. Well, there's a couple of them that might get a little high, but for the most part, higher up you go, colder it gets. Last thing I want to talk about are ocean currents. Now, ocean currents play a huge role in a location's temperature. And the reason why is because there are two types of currents. One type of current is what's called a poleward current. And a poleward current takes warm water from the equator and moves it towards the poles. Any coastline adjacent to that poleward current gets heat from that current. On the other hand, the other type of current is called an equatorward current. In an equatorward current, cold water is being carried from the poles up towards the equator. And if you live near an equatorward current, your air temperatures are going to be substantially colder. A really good example of this is one I took from a different textbook written by two geographers named Luckins and Tarbuck, and they compared Rio de Janeiro in Brazil to Arica, which is just north of Chile. And if you actually take a look, both locations, very similar latitudes, they're both at just about 20 degrees south, they're both right on the coastline, and they're both at sea level. So latitude doesn't really play a difference, proximity to water doesn't really play a difference, elevation doesn't really play a difference. And yet, Arica, which is right on this cold Peru current, is on average about 10 degrees colder throughout the entire year than Rio de Janeiro, which is right next to the warm Brazil current. Now, there's other interesting implications about ocean currents and climate. Another very interesting implication is the area here in Arica. This is actually in an area called the Atacama Desert. Because this water here is so cold, there's very little evaporation. Hence, very little clouds form here. And so Arica doesn't actually get a lot of rainfall. In fact, if you think about how dry it's been here prior to the last couple of years, we still got anywhere between 5 to 15 inches of rain every year. Arica averages 1 inches of rain a year. Very, very dry. We'll talk more about that later though. So that's it for this lecture. Just a quick review in case you wanted to take a quick review. Warmest time of the day, usually 3 to 5 p.m. Coldest time of the day, right at sunrise. And this has to do with the balance between incoming sunlight and outgoing terrestrial radiation. And then the controls on air temperature, elevation, latitude, proximity to water, and ocean currents. All right, that's enough for today. And that's it for Module 2. So begin studying for the Module 2 quiz, and I will see you all next week.